Hello, everybody. Thank you very much for joining my webinar today. We are going to spend the next 45 minutes or so to learn about feature engineering, which is a very important topic for many of us as data science practitioners. Before I get into the details of today's session, I would like to introduce myself. My name is Aaron Chang. I'm the Vice President of Data Science from .data, a Silicon Valley-based technology company doing some cool innovation in the field of feature engineering. I personally have been in this field of data science for 15 years now, spending the first 10 years on the practitioner side and the last 5 years on the technology provider side. In my experience, ODSC has always been a very wonderful venue that brings together the data science community, so that the practitioners can learn from the technology providers on their new development, new technology trend. And the technology providers can hear from the practitioners about their challenges and pain points in their daily work. With that, I just want to thank ODSC again for organizing today's webinar. In today's presentation, we are going to be talking about the three main topics. First, I will walk you through the concept of feature engineering from the perspective of a real-world example, an example that I'm confident that at least 75% of the data scientists out there have had some experience working with as some part of their career. From there, I will be discussing the traditional approach of doing feature engineering and what are some of the common challenges and issues associated with this approach. The last part of the presentation, I will introduce you to a new concept of doing feature engineering that is data-centric by nature. It's what we call programmatic feature discovery. I may not have time to discuss the details of this new technology, but I will be talking about its key concepts, how it works. And towards the end, I will suggest a few ways for you guys to try this technology yourselves. I anticipate my webinar today, my presentation today, will take somewhere between 35 to 45 minutes. And for the remaining time, I am happy to take any questions if you guys may have. So with that, let's get started. First of all, let's talk about what is feature engineering. To better understand feature engineering, it is important for us to, first of all, to look at the overall landscape of a data science workflow. In a real-world data science project, unlike the ones we typically see on Kaggle, where data is ready, you are just being expected to come in and build models. In a real-world data science project, we have to first define a business problem and translate that business problem into a data science problem. From there, we have to prepare data. We have to define data. We have to do the data sourcing. We have to do master data management. And ETL is usually what we refer to for this step of the process. As we all know, ETL type of a data preparation isn't specifically intended for data science or artificial intelligence purpose. That's why oftentimes we have to do a lot of AI-centric, AI-specific data prep and data cleaning. And we have to do feature engineering, which is a process that combines the data to make it ready for machine learning before we can actually build models. Once the data becomes ready, we can build models, we can do machine learning, we can do hyperparameter optimization, we can do model validation. And once we finish this process and come to a model that we are satisfied with, we can deploy these models into production. This is where the ML ops come into play. And here we are doing model scheduling, for example, model monitoring, model retraining if needed, that kind of fun stuff. Truthfully, if you look at this entire process, there is a lot of technology advancement that has been made in the field of ETL, right? The Informatica, Paxata, Trifacta, to name a few. There is also a lot of new technology, open source technology, especially in the field of machine learning, in the field of ML ops. But feature engineering is a field that we don't have as many new tools, new technologies about. And this is why, for many of us as data science practitioners, we know that feature engineering is and it remains a significant pain point for us to deliver machine learning projects. And that's what I'm going to focus on today. To best explain how complex and challenging this feature engineering can be, I'm going to start with this real-world example that we are going to do a customer churn prediction. This particular project is actually a project that I have been personally associated with. I remember 6 years ago, this banking customer, they came to us. This is a customer that they offer a variety of consumer banking, credit card banking, and mortgage products. And they have collected many data sets related to their customers in each one of these business areas. And currently, this data is just sitting in their enterprise data warehouse. Their credit card team come to us. They want to know if they can leverage this data to build a machine learning model that can help them understand which credit card customer is going to churn away. By doing that, hopefully they can stabilize their business, retain their customers, and maybe come up with some ideas about how they can further improve on their credit card products. Once this kind of predictive model is built, they anticipate a business dashboard to be constructed. In this business dashboard, they will automatically display who are the higher risk customers, what are the factors leading to their churn, so that the sales and marketing team can react to that information on a weekly basis, or maybe even on a daily basis, to those higher risk customers by offering them some incentives to keep their credit card. This is a very, very common use case. You might have not worked on a customer churn use case for a bank, but I'm sure at some point of your career, you have done something, like this kind of, you have solved this kind of problem for a retailer, for a manufacturer, and so on. No matter what kind of specific churn prediction you have worked on, the business context may be different, but I'm certain that we have one thing in common here. And that is, your data usually starts with what we are seeing here. There's many, many tables available. Some of them are simple, some of them are complex. Some of them are large, some of them are small. Some of them are static information, some of them are transactional information. All of them are conceivably related to the customer churn behavior, but in what specific way? You are not sure. And what's more challenging is that this data, this distributed data, right, currently prepared in a normalized way, sitting in enterprise data warehouse, this is not ready for machine learning models. In order for machine learning models to work, no matter if it's a traditional machine learning model or state-of-the-art deep learning model, it requires the data to be prepared in this single table, XY format. In this case, all the X variables are what we call the predictors, and the Y variables are what we call the prediction target. The data has to be prepared in this specific format so that machine learning models can work. Then the challenge here is, how can you combine all these distributed tables to prepare this XY table format? And that is the challenging. And that is what we call feature engineering. So with this, I want to walk you through this process of solving this problem, right? As I just mentioned, we have 10 tables to begin with. We know that they are all relevant to the problem, but specifically in what way, we don't know. Then how do we get started? We don't start with all 10 tables together, but we start with something that's more manageable. We start with 2 tables, right? In these 2 tables, obviously, the credit card churn table, which is a table that captures the customer's historical churn information, is important. This is what we call the target table, right? And also, if we want to predict which customer is going to churn, it is very natural for us to start with some higher level of customer information. This is why this customer demographic information table is important. If you look at these two tables, right, for every customer that's shown in the credit card churn table, there is only one unique record for that customer in this customer demographic table. This kind of a one-to-one relationship between these two tables makes joining these two tables together fairly straightforward. In SQL terms, essentially what we do is according to the common ID, which is the customer ID, right? One simple join in SQL can combine these two tables together. So this is the two-table feature engineering. If you start with these two tables, if you have to develop this single flat feature table that combines the information from these two single tables together, it's actually fairly straightforward. All you have to do is just one step of a SQL joining. Right? It's very, very straightforward. The challenge, however, is that if you were to build a machine learning model using the features coming from only these two tables, the machine learning model performance may not be the best. Essentially, we are being provided with 10 tables. We are only using 2 tables of information. Obviously, we should do better. Right. Now we should add the next table, right? We are interested in predicting customers' credit card churn behavior. It's very intuitive for us to consider, right? Customers' credit card usage information. If someone that is very active in using this credit card, the chances for that customer to churn away is smaller, obviously. Then how can we add this information into the mix so that we can build a better model? So this is what we are going to be talking about. Now I'm going to add the third table, credit card payment information. But this credit card payment information is actually a little bit more challenging compared to previous 2 tables. The challenge is that for every customer that we are looking at in this credit card churn table, there's actually many records for that customer in this credit card payment table. Essentially, this credit card payment table is a transactional table. There's a timestamp. Every time there's account balance due, there's a new record. For the same customer, every time there's account balance due, there's a new record. Every time there's a payment being made for that customer, there is a record. So that's why there's many records in this credit card payment information table for this given customer. Now, if we were to look at this 3 tables together, essentially we are having a one-to-many type of a relationship. Right? In this kind of situation, it's not very easy to directly copy this credit card payment information for a given customer into the credit card churn table, simply because, as I said, there is more than one record. Which record of information are you supposed to copy to in this credit card churn table? Right. In this case, the way we need to, the approach to solve this problem is we need to figure out a way to reduce the amount of records in the credit card payment table so that we can easily pass this information back into the credit card churn table. And the most typical way of doing this kind of data reduction in the field of statistics is to perform aggregation, to perform the time-based aggregation. Right? The aggregation can be the summation, the average, the minimum, the maximum, the standard deviation. In this case, we just need to define a time window and perform this aggregation. By doing that, we can reduce the amount of record from multiple records into one record. However, the challenge is, what is the right type of aggregation we should be applying? What is the right aggregation time window we should be considering? These are all non-trivial questions. And the real challenge is more than that. When we are dealing with this kind of time series data, there is a constant hurdle, and that is called the time leakage. What is time leakage? Let's look at this credit card churn table, which is a target table here. We are interested in predicting customers' churn behavior. Let's say for this particular customer, 13515. We are interested in predicting for this customer at March 2022 if this customer is going to churn. Right? When we are trying to make this prediction, in principle, we should only be using the information collected for this customer before March 2022. All the information that is captured after March 2022 will not be available when we are running this prediction. If we are using that information to build a model, to build a feature, we are introducing this time leakage. However, if you look at this credit card payment information table, this table captures for this customer 13515 all their credit card payment information that is starting from January 2022 all the way through April 2022, because this is a transactional table. Every time something happens, it will just insert a record. Then in this case, in order to build the right feature for this particular problem, how do we select the right time range, right? So that we can use the right amount of data to build a feature. That's the issue of time leakage. If we don't solve this problem correctly, we may build the best model, but that model is a faulty model because it's using certain information that in reality would not be available when we are making the prediction. How to solve time leakage problem is a big one in the field of a time series type of machine learning problems. The other one is if you look at this credit card table, credit card churn table, in this case, the time information is captured on a monthly level. Here we are talking about March 2022, February 2022. But on the other hand, if you look at this credit card payment information table, the time information is actually captured at the daily level. It's instead of captured at the January 2022, here we have a January 31st, 2022, February 28th, 2022. So these two timestamp information, they are at the slightly different time resolution. One is on the monthly level, the other one is on the daily level. How can you harmonize these two different time resolution so that you can put them together? It's another manual effort you would typically have to go through. For example, you need to manually convert this daily information to a monthly information before you can start doing the joining. These are all the manual challenges that one has to go through in order to consider how you can combine all of this table together. However, I have to say that if you are a data scientist that really understand the business, if you are a data scientist that is working very closely with the business expert, I think all of these challenges can be addressed. For example, what is the right aggregation function to apply? What is the right aggregation window, time aggregation window we should be applying? The typical way of answering that question is start with considering the business context, right? Deriving some business hypothesis. For example, one business question we can ask is, are these people active credit card users? If they are active credit card users, maybe the chance for them to churn is less. If that's the case, how can we quantify the activity for our users, right? Maybe we can do something like an average account balance for a given user in the past 1 month, in the past 3 months, in the past 6 months. So this is how we start thinking about what kind of aggregation function do we apply. We can do the same thing for how much do they spend per month? Are they missing any payments, etc., etc. The point is when we are dealing with this kind of 3-table feature engineering, it's difficult, obviously, it's tricky. But if we start from asking the right business question, I think it is possible for us to derive features. It is possible for us to generate this single table, XY table that can be used for machine learning. So that's the point here. It's already difficult, but it can still be done. But the real challenge is if we want to keep adding more tables, because we are being provided with 10 tables. We are only using 3. We want to improve our model performance. Like in this case, we want to add the 4th table, customers' saving account balance information. Obviously, this saving account balance information will give us some good information about the customer's overall financial well-being, and that should help us in predicting this customer's credit card churn behavior. If this is the case, right? Say this account balance table, how can we add this table into this previous 3 tables so that we can build a feature. If you look at this account balance table, this is another time series table. Now this problem becomes exponentially complex. Right? Combining 2 time series data is actually extremely messy. There's this time leakage issue, then there's this time resolution issue as we just discussed. But the real challenge is that there's just way too many ways to combine 2 time series together, right? Thinking about the interaction between them. And this is a challenge. This table, account balance table by itself, it's fairly straightforward. It's just another credit card payment information, another time series table. But when you are having another time series table on top of the existing time series table, this is where things becomes really, really messy. We can still try to use the approach that we just discussed, asking the right business questions, trying to get some business ideas to tackle this problem, right? For example, we can ask questions like someone has a lot of money in the bank and has not used our credit card in a while. We can also ask different kind of questions. Someone has a monthly deposit over $5,000 and who is an entrepreneur. Someone that has no money in the bank and has a large credit card debt for some. We can ask many, many questions like this, but the challenge is given there's 4 tables, given both, there's 2 tables that are time series by nature. There are just countless ideas like this. Then in the end, which idea is the idea we should pursue? Because for each one of these ideas, someone needs to build a very complex SQL in order to implement these ideas into features. And given that there's countless ideas, I think this entire workflow just becomes unrealistic. At this point, I think we should agree, when we are talking about the 4-table feature engineering, when we are talking about multi-time series, in this case, manually building features, manually exploring this data to try to build a machine learning model is become impossible. Okay. But the real data is that we have even more than 4 tables. Actually, we have 10 tables. Right. If you look at all these 10 tables, there's a credit score information. Right. You would think that's a very important information for credit card customers. We should use that. There's customers' web browsing information that tells you how active this customer is with their bank's apps on their phone. That tell them how interested, how active, how engaged this customer is with this credit card product. That could be useful. There is this customers' reaction to the past marketing promotions to the credit card team. That can be a very good information as well. Every single table seems to be important. But as I just explained, up to 4 tables, I think we are already stuck how we can combine them together. But the real situation is when you have 10 tables, how can you practically combine all this information together that can help you build a machine learning model? So that's the challenge of a feature engineering. If I were to trying to summarize what kind of what feature engineering really is, I think I want to break it down into 2 steps. The first step is kind of what I just described. In a real enterprise data situation, right, you have many tables distributed in a normalized way across different tables. Then for feature engineering, the first step is that we need to combine all these individual tables into a flat feature table. And in doing this, there's many processes one typically need to go through. For example, we need to do this data quality and data cleansing work. We need to do data schema matching. We need to do missing value and outlier treatment. We need to do this, for example, when data is highly skewed, how do you deal with this kind of data skewness from statistical perspective? And most importantly, in this process, we need to do data combination. We need to join tables. We need to turn the 10 tables into one big table. In this case, we do the normalization and denormalization. We need to deal with what is the right aggregation one should be using in doing this data combination. How do we deal with the temporal information, etc. So this is the first step of feature engineering. It's primarily about combining tables into a flat table. The second step of feature engineering is when you have a flat table, how can you generate additional information based off of this flat table? And in this process, we know that typically for a categorical attribute, we do categorical encoding. For a numerical attribute, we do numerical data binarization. When we have timestamp information, we can generate the timestamp-based features like a holiday type of information. Right? And also, this is where we can do a lot more than that. We can apply the polynomial transformation to build those mathematical features. We can apply neural encoding to generate more complex features. We can even do dimensionality reduction to generate some of the features that are less noisy by nature. So this is overall, if I were to look at what feature engineering is, essentially there are just two steps. At this point, I think you guys probably see that the feature engineering is probably a lot more complex than we realize. Then if it's so complex, if it's so time consuming, why do we have to do feature engineering? Right? In my understanding, there are two key reasons why feature engineering is essential. The first one is actually business insights. Right? Even though we are building machine learning models, but in the real situation, we all know that prediction outcome is important, but business insights may be more important. Like in this case, we are trying to predict which customer is going to churn. If we are only running predictions, we can give this a list of customers that were likely to churn to our marketing team or sales team. They look at that information, they'll be like, okay, this is a little bit too late. What can I do about it? However, if we tell them for what reason this customer is going to churn, that information can be more helpful because that information can be preventative. They can take advantage of the information to do something to prevent the customers from churning. Like in this case, let's say if we identify a feature that is someone's credit card balance decreased 75% during the last 3 months. If say this is one key feature, right, that is driving customers' churn behavior, the marketing team, sales marketing team, they can look at this information. They can say that maybe we should monitor people's credit card spending behavior on a rolling 3 months window. Whoever has a declining pattern, by 75% during that time window, we should go to them, maybe offer them some kind of a incentive so that they can stay on with this credit card product. So this information actually becomes a lot more useful to the line of a business rather than just giving them a prediction score. The other reason that why feature engineering is important is because better models. Obviously, we all know that in the field of data science, more data, right? Oftentimes resulting in a better model. Like in this particular problem, as I explained, if we only use customers' demographic information, there's only so much predictability that we are talking about compared to when we are starting to introduce the customers' credit card usage information, when we start introducing customers' bank account information, when we start introducing customers' credit score information. There's just a lot more information that we can use, all of which will help us construct a better model. And that is why feature engineering is important. So with that, I want to get to the second part of the presentation, which is I want to discuss a little bit about this traditional approach of doing feature engineering, right, which we call manual feature engineering. I touched upon this a little bit earlier. Manual feature engineering, essentially, it is a process that is primarily driven by business ideas, by the business hypothesis. To really understand how manual feature engineering is working, it is good for us to understand who are involved in this feature engineering process and how they are working together towards building features. And with this, I want to start by making this statement. And that is that in most enterprises, features are at the interface across different stakeholders. And this is not exaggerating. if you look at who are involved in this process, right? Domain experts, they know their business. They know their data. They know what are the key information they want to use in driving their business actions, and that is features. And data engineers, they take the ideas from the domain experts to build stable pipelines to generate features. But data scientists, their job is to evaluate the features that is constructed by the data engineers. Actually, if you look at these three parties, they are all working towards part of this entire feature development. And this is in action how this manual feature engineering is working. It typically starts with domain expert. As I said, they have the knowledge, right? They know the data. So they will start with saying, I know the data, I have some ideas. These are the leading hypotheses. Let's start with this. Then they give that idea to data engineers. Data engineers will implement those ideas, building a lot of SQLs, and then turn them into features, put them into some feature mart or some kind of data warehouse. And then they give these features to data scientists. It is data scientists' responsibility to evaluate these features, right? To test their statistical performance, test their robustness, and maybe even building some preliminary machine learning models. And then after that evaluation, they will provide the feedback to domain expert. I like 1, 2, 3. You know, this particular feature hypothesis may not be relevant. For some reason, the data is limited. It doesn't really support the other ideas you have. That kind of a feedback going to the domain expert will be incorporated by the domain expert when they come to the next round of a hypothesis. All right, with that, they modify their ideas, they keep ideating, they pass new ideas to data engineers. Data engineers will modify their feature pipeline, maybe even building more newer features, and then give those features to data scientists. Data scientists keep evaluating, keep providing feedback. So this process never ends until we come to a point. For example, we arrived at some kind of model predictive performance, right? Say 80% of AUC score, right? Right now, given what we have done, our model is ready at 80%. Maybe that's when people can stop this process. But in principle, this process just continues. It's a feedback process, and that's why this manual feature engineering process by itself is iterative by nature. Now let's look at this specifically how this is done in action, right? Say the domain experts has one idea, right? Do engineers who withdraw a lot of money in the past months, do they like to churn, right? So the idea may be very simple. Engineer is a tech engineer is a good paying job. Engineer that withdraws less money maybe means potentially they are using a different kind of financial product, maybe using a different kind of credit card product. If that's the case, maybe they are interested in a slightly different kind of credit card product offerings, right? So, if this is a hypothesis, they want to test this hypothesis, they would give this idea to data engineers. Then the data engineers would have to manually construct a SQL to implement this idea into the features. As you can see, this is not the most complex SQL you've ever seen, obviously, but this is also not an elementary level of a SQL. Right? There's a fairly complex joins, left join, there's a cross join, there's a lot of nuance in the SQL as well. But the point is, if you have only one idea, like in this case, do engineers who withdraw a lot of money in the past months churn? If you have only one idea, it's okay. We can build this SQL and then we can evaluate it, we can test it. But given the data we are looking at, we've got to have more than one idea. Now we have the second idea. Our customers aged 25 to 45 who responded to a promotion in the last 6 months and live in a specific zip code, less likely to churn. This is a very different idea. It requires a very different kind of a SQL. Now, data engineers take this idea, build this second SQL that is dramatically different from the previous one. But as we all know, there are two challenges here. One is how many ideas do we realistically have in a real enterprise kind of a data? It's more than one, more than two. Oftentimes we are talking about hundreds, if not thousands. And also not every idea works. Right? We need to test each one of these ideas. If testing each one of these ideas requires the implementation of all the SQLs, right, one by one, obviously this process is not sustainable. And also, where do all these ideas come from? These are all the challenges associated with this kind of a process. We all know that the domain knowledge is the most critical piece of information on any given machine learning project. Right? Asking the right business question is the most important thing for us to consider. However, in a world that we live in today, where there are new data sources keep emerging, right? There's a lot of data that we probably don't have enough of knowledge about. In that situation, how do we get started? How do we get started? Do we really have time to go through all those iterations, right, in order for us to understand those new data sources? That's one challenge, obviously. The other one is that the business situation is rapidly changing in the world that we currently live in. Before pandemic and after pandemic, many industries, their business is fundamentally changed. We have a lot of domain knowledge about what has happened in the past. If we just apply that knowledge into today's problem, we are maybe introducing a lot of assumptions, right, into the analysis. And that really limits the capability of the models that we are looking at. Another challenge with this kind of manual feature engineering is that, it's very, very natural for us to build a feature one by one, because this kind of organic process is essentially how development works. But the challenge is how many times have we built average sales amount for the past 2 weeks type of features for your data science projects, right? I personally have built these features over and over again, no matter I am running a prediction for a store sales forecasting or product sales forecasting or regional sales forecasting. Essentially, it's the same kind of feature that could have been used for very different kind of a predictive analytics projects, but we are not treating this feature as an asset. That's why every time we solve a new problem, we build it, but we are not making this a reusable asset. And the challenge of doing this is that it's a SQL after SQL, notebook after notebook. It's all for one-time use. And this really creates a headache when it comes to the productionization. Building a one-time code is very easy. Keeping it up is actually very hard because data keeps changing. Because you constantly get feedback from your business experts about how to improve your features. You are being constantly asked to incorporate new data sources into your notebook. And every time you make a change, right, you have to change your SQL. You have to change your notebook, like what we are seeing here. We have df, df2, df underscore 2, df underscore final, df underscore final. It's just endless, right? So all of this, it's very, very natural from a development perspective, but it's just a sheer chaos when it comes to productionization. What are the dependencies, right? Which notebook is a ground truth? Actually, it's completely lost. And that's another key challenge with this type of manual feature engineering. With this in mind, I would like to briefly introduce you to this new concept of programmatic feature discovery. That is data-centric by nature. As I said in the beginning, I don't have enough time to go through the details, but I will tell you what this technology is all about and how it works. And I will introduce a way for you guys to try this technology towards the end. What is the programmatic feature discovery? In simple terms, it's a way to let the data speak for itself. when defining features, right? In the past, we rely on the business hypothesis to get this process started. What we are doing here is we want the data to speak for itself first before we apply domain knowledge. The way it's working is that you need to first of all describe what your data is to the technology engine. Okay? And then we said the technology engine will automatically generate what we call the feature space. Essentially, it's a millions of feature ideas that are relevant to your particular data. And then the technology can further suggest a couple of features that are more relevant, a couple of features within this millions of feature space that are more relevant to your particular business problem. Then with that, domain expertise come in. The domain expertise can help you evaluate these features, evaluate the feature space, so that you can fine-tune the features, you can modify the features, you can even create your own features, so that you can come up with this final feature pipeline, which you can use for machine learning. So that's sort of in a nutshell how it works. Right? There are 3 key steps. The first one is define what is your target, what is your prediction interest, and what is entity relation between all those data sources that you are interested in. That's the first input. The second one is with this input, the programmatic feature discovery engine by itself will explore all potential features and provide this feature space definition for you. Right. Then with that, we can select features, we can modify features, we can even build our own features, and we can construct a feature pipeline. Going through all of this, we can come up with the features that are relevant to the particular problem we are interested in, and that is the feature table. And this feature table can be directly fed into this business dashboard that we are interested in, right? So with this new approach, instead of waiting for the domain experts to provide all the knowledge, going through that manual process of building features one at a time, ideating features one at a time, we can rely on this programmatic feature discovery engine to tell us the most important information. And on top of that, we can apply our domain knowledge. So this is a very different way of doing feature engineering compared to how I described it in the earlier part of feature engineering, in the first part of the presentation. And right now, I want to introduce the .Data's Feature Factory because we are a pioneer in this field. .Data's AI-driven automatic feature discovery tool can really help you identify the most impactful features related to your target variables. We have had many customers who have really benefited from this technology. By applying our technology, instead of spending months and months going through their data, building features before they can even build some basic models, within .Data, they can just spend a couple hours. We can give them the preliminary set of features so that they can apply their domain knowledge on. And with this, they can really get to their result a lot faster. Right? They can really deploy their features a lot easier. They can really see the business impact of their predictive projects a lot sooner than their traditional approach. And our technology stack is very, very versatile. We can work with different kind of infrastructure. Essentially, it is a Python library that can be deployed into any kind of a data science workflow that you guys currently have. So these features can be directly put into machine learning models. It can be stored as feature assets into feature stores. If you guys are currently using feature stores, some of the features you can directly even put them into the business dashboards if that is of interest. So overall, from the from the capability point of view, we really work with many different kind of technology infrastructures and have very different kind of applications that can be developed around it. So with this, I want to tell you that we have this program that is currently offered to our early adopters. If you guys scan this barcode, you will be directed to a page where you can sign up for a free access to this product, and you can try it on your own projects. or we have an awesome training program as well. You're welcome to try this product according to our training program. So with that, I'm gonna end my presentation today. I encourage you guys to try this product to see how it can help you deliver your projects faster, how it can help you to deliver the business impact that you are looking forward to. With that, I'm happy to take questions if there's any. Thank you.